Consider multiplication. Multiplication is one of my top 4 operations, but I think for mathematicians it ranks number 1 in their hearts, because they've decided to give it a myriad of snazzy styles. You have the classic 3 times 5, the new age 3 star 5, the minimalist 3.5, and the pragmatic 3 parentheses 5. But perhaps most taken for granted is how multiplication sometimes needs to be read between the lines. If you take 3 and you put an x next to it, you just unintentionally multiply without even having to use a symbol at all. And this has major implications for the world of writing. Every time you thought you were writing words, you were actually multiplying. That 1,000-word essay you forgot to write saved thousands of calculations. But today I want to do those calculations and find the true objective value of our words. One of the issues with trying to do all this multiplication is that mathematics allows us to set variables like m and a to whatever values we want. We could use their position in the alphabet, which would put m as 13, a as 1, t as 20, and h as 8, giving us a value for 2080 for the word math. But this solution doesn't feel very universal. In order to solve for math itself, we need an enclosed system without the assumption of a pre-existing alphabet. Luckily, math has what's known as numbers, and they can help us a lot here. We know that the numbers have existing values that can't be changed, so we only have to figure out this multiplication problem in order to solve for the different letters. So let's see, we need 1 and 9 to work. So we can have n be 3, and then o can be a third. So then I and e have to be 1. And in order for 10 to work, we need t to be 10 over 3. And if we want 2 to work, then we have to have w as 9 over 5. And then there's 3, which has an h and an r in it, but 4 also has an r in it. This problem is getting kind of complicated. Maybe there's a more mathematical way we can approach this. And sure enough, looking a little deeper into the world of mathematics, it presents us with a framework in which to consider the problem. What we have is called a system of equations. Some number of equations and some number of variables to solve for using the equations. Typically, in a system of equations, you want the same number of equations as there are unknown variables, which will ensure that there can't be infinite solutions to the problem. To understand why, consider the system 3x plus 2y equals 5 and 7x minus 3y equals 4. We can rearrange these equations to solve for y in terms of x. And then we can actually plot both of these on a graph. And you can see that these two lines intersect each other at one point, and just one point exactly. And this is the one solution to the system of equations. It's at x equals 1 and y equals 1. But imagine we were to add a new variable z. This would extend the graph into the third dimension, and each of these lines in 2D would become infinite planes in 3D. The entire line where they intersect would all be valid solutions to the system, unless we were to add another equation which creates another plane and just one solution, where all 3 planes intersect. So a logical first step is to try to find the point at which the number of equations equals the number of letters within those equations. So if we start with 1, we've got three letters in the word 1, and then we've added on 2, which adds 2 more, so that's 5 letters. 3 adds the H and the R, so that's 7 there. And then we have 4, which adds the F and the U, so that's 9 letters. And 5 adds 2 more, giving us 11. 6 adds 2 more, 13. You'll notice none of these so far have got the same number of equations as unknown, so we have to keep going. 7 doesn't add any more letters. 8 adds that G, so we've got up to 14. And then we don't get another new letter until 11, which adds an L, giving us 15. And then the next letter that gets added is actually all the way up at 20, where we get a y. So we've got 15 letters we need to solve for by the time there are 15 equations. And so that is the point that we want to solve. It's the point where they have the same number of equations as unknown. So hopefully there will be one solution for each letter, and we'll be able to get all the letters up to 15. So I'm actually pretty excited. But how do we solve for these system of equations? Well, in school, they taught us two methods, substitution and elimination. I'm pretty sure elimination won't work here because it needs to subtract terms, and unfortunately all our variables are getting multiplied. So it looks like we're going to have to use substitution instead. Except if you've ever used substitution, you know that it's really annoying to do, especially with more variables. Like I remember taking 20 minutes to solve a problem with just 3 variables. And you're telling me I have to do this with 15, and I don't even know if it's possible? There's got to be a better way. Of course, we're going to consult Google here. How to solve big systems of equations. Alright, elimination method, we can't use that. Oh, solve a larger system of equations by matrix. This could be it.
Okay, in this video we're going to be solving this system by using matrices.
Okay, so a couple problems here. The first one is that this is not a very large system of equations. This is only 3 equations. But the second one is that you can see that this whole system is added and subtracted, each of these terms, and in our system of equations, they're all multiplied. So I'm not sure if the matrices are going to be working for us, but perhaps we can find something unique. It seems like we're kind of stuck between 12 hours of substitution and failure. But perhaps math has a solution for us once again. Who can we call up to help us on this endeavor? I know. I can call my good buddy logarithms. See, logarithms have this magical energy that allow us to kind of lower the intensity of operations. What was once exponents is now multiplication, and what was once multiplication can now become addition. So you can have 2 times 3 equals 6, and if you take the log of both sides, you can have the log of 2 times 3 equals the log of 6, and then we can use the way logarithms work to say that the log of 2 plus the log of 3 equals the log of 6. This is one of the basics of log rules. This kind of feels illegal, but it is true. So now we can take our multiplication system of equations and just turn it into an addition system by taking the log for both sides. And I'll be using the log with a base of e, which is written as ln, just because I feel like making this more complicated than it needs to be. So we can write all these down. We have ln of o, n, and e equaling ln of 1, which is actually just 0. But once we have all these equations written as logarithms, how do we solve it? Well, we can employ the use of matrices to solve simultaneous systems of linear equations, and now we have our system of linear equations with all these ln's added to each other. So let's figure out how to use the matrices to solve the system of equations. So matrices are kind of interesting in how they multiply. Each row of matrix 1 is multiplied by each column of matrix 2. In the case of a system of equations, the second matrix is just one column of unknown variables, and the first matrix contains lists of the coefficients of the variables, with the rows corresponding to each equation and the columns corresponding to each variable. In this small example, you can see the x column on the left with 2 and 3 being the coefficients for x, and the y column on the right with 5 and negative 6 being the coefficients for y. When you multiply this matrix out, you get the same system of equations that generated it in the first place, meaning that this matrix representation is equivalent to the system of equations. So why did we go through all this trouble to write the system of equations in a more confusing way? Well, now that we have this matrix representation, it's very easy to rearrange the equation to solve for this x and y matrix. So you're not actually technically allowed to divide matrices like this because you can't actually do that. But what you can do is rearrange this into a multiplication problem between the inverse of the square matrix multiplied by this answers matrix over here. So the only thing left to do is to solve for this inverse matrix over here. But it's actually kind of difficult to solve for that as well. It's not as simple as just taking the reciprocal of each term. The inverse matrix is such that when you multiply it by its non-inversed counterpart, you get what's known as the identity matrix. The identity matrix is kind of cool because if you multiply it by any other matrix, you get the same matrix back. If it were a matrix generated by a system of equations, then the system would already be solved because it would be 1x plus 0y equals something and 0x plus 1y equals something. So how do we solve for this inverse matrix? Well, we could build a totally new system of equations with 4 equations and 4 unknowns, and that sounds like the dumbest idea ever. But we could also multiply the determinant by the adjoint of the matrix, and there might be some day in some math class where they force you to solve for that. But it's 2022 and we have computers, so that's what I'm going to be doing. So back to the problem at hand. We're trying to find the values of all these letters, and so here I've constructed the matrix 15 by 15. This is the matrix equation that we have to solve, and actually it's a little bit inaccurate because you've got this column here with all these letters, but those are actually the ln values of the letters. If you remember, we have to turn everything into ln's. So when you have that 1 on the top left corner, that's actually 1 times ln of e plus 0 ln f. So those letters, once we solve for the values, we'll just do e to the power of that value, and that'll be the real value. So yeah, let's solve for this inverse matrix. I'm super excited. No, I'm not. I hate this. Alright, so here we have the inverse matrix calculator on whatever website this is. You can see my struggles. Anyway, let's crank this up to 15 here. Looking pretty good. I've got all the numbers copied, and here we have our matrix, and now we just gotta find the inverse. Here we can see our first issue here. It seems like not all square matrices have an inverse. So it makes sense that not all matrices have an inverse because not all systems of equations have a solution. For example, if x plus y equals 5, then 2x plus 2y has to equal 10. But on the other hand, if x plus y equals 5, then 2x plus 3y could be literally anything. When two equations are deterministic like this, they are said to be linearly dependent. Remember how two linear equations, when graphed, intersect each other at just one point? Well, the exception to that rule is when the lines happen to be parallel. And that's exactly what linearly dependent lines are when you plot them on a graph. As we add more equations, there's a higher chance for linear dependence, because the new equations not only have the chance to be linearly dependent with old ones, but they can also be linearly dependent with a combination of multiple other equations. For instance, in a system with 3 equations, the third equation has the possibility of being parallel with the line created by the first 2 intersecting planes, which would also cause the system to fail. In the case of our 15 equations, the one causing the issues is 12. Something about the combination of letters it has makes it linearly dependent on the equations of 2 and 11, and its value, when multiplied out, will always be 22. This unfortunately makes it impossible to come up with values of the letters to make the numbers 1 through 12 work, which is really sad, and I think we should consider changing the name of 12 to duodes, or something just so this can work. But in the stead of wallowing over no longer contained mammal juice, I've decided to just ignore the number 12 for this project and to add the number 16 so that there's still 15 equations and 15 unknowns. And it also turns out that the numbers 14 and 16 are incompatible with each other because of reasons. So I decided to spell 14 without a U because that's still 14, and now everything works. We can finally have our inverse matrix at long last. Now we just have to take our inverse matrix and multiply it by a matrix containing the first 15 natural logarithms, but except skipping 12 and going to 16. And that'll give us a matrix with the values of the natural logarithms of the letters E, F, G, H, I, L, N, O, R, S, T, U, V, W, and X, which are the only letters in the spelling of the first 16 letters. Wait, numbers. Whatever. So I did that, and then to get the actual values for these letters, you have to do e to the power of each of these numbers. And so now I have the objective value for each of these letters. Here they are. And just take a look at how wacky they are. You can check to see if every number 1 to 16 works, except for 12. I don't actually know if any of these numbers are rational, or how to find out. Actually, wait, they probably are all irrational, since like it uses the logarithm. Ln of 2 is irrational, and so is ln of 3 probably. And so these are probably all irrational, infinite decimal numbers, and should be worshipped just like pi, but also associated with their letter. People could memorize the first 100 digits of L and W, and then when you beat them in a game, you could say they took you could say you took the 4.153847445, and they took a 1.459485535. The possibilities are truly endless. I programmed the values into my TA84, and now I can do math by spelling. And we can also use these numbers to evaluate other words to see what their value is. But before I can know the value of math, we need to add the bonus features. So while the numbers 1 to 16 is cool, but what if I want 60? Well, anything with a ty at the end is generally just that number and then multiplied by 10. So if I make t times y equal 10, then 60, 70, 80, and 90 will all work. And 40 if you use the u you stole from 14. And y is a free letter because it wasn't used in the construction of 1 to 16. So that's an easy 4.557328485. We can do this with hundreds too because d is free. So you can spell 300 without spaces, and so long as the word 100 equals 100, then all the hundreds will work. So d is equal to 1.223905032. 1000 has a free a, so a equals 93.85703.183. Millions m is let's take a look at this. 9,375,341.51732. I also want p to be pi because that's funny, and I want the entire alphabet to be 42 when you multiply it. So let's make z 6.8036469 times 10 to the negative 16th power. Now we can do even more math by spelling, but more importantly, we can now finally figure out the value of math. It's 1.082513134 times 10 to the power of 10.